Hey, so from the conclusion from our prereq video on Jacobians was that, hey, the area of the xy parallelogram is just equal to the area of the UV rectangle multiplied by this determinant, which would, simplify to AD minus BC. And, if you think about, when you scale this, right, that just means that every, kind of dA element in the xy plane, right, if you think about this is equal to dA, is just going to equal the dA elements. I can call this like dA, I can call this maybe like dA prime, right? So the area elements are proportional to each other, right? They're scaled by this determinant, and that just means dx times dy, that is dA, is going to equal this determinant times du times dv. Why would I care about that? That seems like a kind of weird conclusion. Well, what we've done in the past is we've kind of taken a look at U sub in Calc 1. So in the 2D world, if you want to call it, we had this, you could solve this integral by saying, hey, let U equal sine of x, right? And then du is equal to cosine x dx, right? Now, this is kind of interesting. You're saying du it's gonna be proportional to dx in some way, or hey, wow, that looks kind of familiar. What you would do is you would then have this be u squared du, and what happens then is your bounds change, right? Because now you're in the u world, right? You're integrating with respect to u. So if you were to translate this, right, if you were to transform these bounds from the x-axis to the u-axis, that's as simple as just plugging in 12 as x and then 4 as x, and you would get like sine 12 and sine 4, right? Which I don't know those values, and that's kind of weird numbers to pick, but you get the idea. Sine 12, sine 4, you've transformed the bound, right? So if this is maybe, right, if this is sine 4 and then sine 12, or 4 to 12, then we've transformed it, if this is the x-axis, we've transformed it from sine 4 to sine 12, whatever those may be, right? So this is the u world. I've transformed it. Now, hey, when you're doing, if you want to do a change of variables, this is what we call a change of variables. If you want to do that with double and triple integrals, then hey, how do you go about doing it, right? You would essentially sub in something for u and you would sub in something for v. But now, because you are essentially, changing two variables, you're no longer just changing the, before the kind of region of integration in the 2D world with a single integral was just the 1D kind of bounds, right? The one-dimensional kind of what you're integrating along the x-axis. The two bounds kind of change. Now, with two variables, what changes is the region, right? The 2D region that you're integrating over. So that's what we've done. We can change the region into something simpler. We did u sub last time to kind of make the integrand, or whatever we're integrating, we did u sub to make it easier. Now we're doing this change of variables to make the region easier. And this determinant, if you notice something, hey, if we look at these equations of transformation, what's partial x, partial u? That's just equal to a. What's partial x, partial v? Hey, that's b, right? Because these are linear equations. Partial y, partial u is equal to c, and partial y, partial v, sorry, I got lost there because I'm thinking about how I'm going to explain this, is equal to d. So really, this determinant is actually just partial x, partial u, partial x, partial v, partial x, partial y, partial x, or u, oh my god, I'm so sorry, and partial y, partial v. This is what we call the Jacobian. The notation is something like this. I think this is the notation. Don't get too lost on this. It looks like you're taking some sort of derivative. This literally just means Jacobian. we call this matrix the Jacobian in honor of a mathematician who I'm not too familiar about because I'm not really big into math. But yeah, this is what we call the Jacobian matrix, and this is our scaling factor. Let's do an example. Let's see this in action. There's a whole, this is a whole lot of like, oh, you're changing the region. Well, let's actually look at see how this works in practice. So I'm gonna get an example problem really quickly. So let me just go over here. Let me just pause this. Okay, so we have a parallelogram, or we want to integrate 4x plus 8y, double integrate in a region, in a parallelogram with these vertices, right? So -1, so let's just first really draw this out. So -1, 3, so -1, 3. 1, -3. So 1, -3, kind of the opposite. And then we're gonna have 3, -1, and then 1, 5. So it's this parallelogram, right? Let's think about this. This is not, if you go back to double integrals, this is not a type 1 or a type 2 region. It would be kind of, you could actually make this into a type 2 region, but it would, you'd have to split it, and then you'd have to, we don't want to do all that. There's another way we can go about doing this, by transforming, by substituting x and y in terms of u and v in a way that makes the region easier. So let's think about these equations of these lines right here, right? This is a parallelogram, so we know these two sides are parallel with the same slope. These two sides are parallel with the same slope. Let's find this slope really quickly. So we can kind of label these A, B, C, D. So slope of B and D. What we can do for D, we could just use, so if this is, so we would just use the slope of this point versus this point. So for this point, it's going to be -3, and then this point right here is 3, and then we're going to have from 1 to -1. I'm so sorry about that. I'm going to sneeze again. I don't usually sneeze. That's so weird. Wow. Felt good, kind of. So this is -6/2. This just becomes -3. Am I going to sneeze again? There's something in the air? I don't know. So this slope right here is -3. Now let's, we can just find equations of lines, right? We just think of a point. So the point, if you use point slope form, y minus 3 and then equal -3. I'm going to sneeze again. Why am I sneezing? X plus 1, right? Oh my god. I've never sneezed so much. Okay. So I have y minus 3 equals -3x minus 3. The minus 3's cancel off. I get y equals -3x. For this point, I'm going to do the same thing. Y equals, so this point right here is 5, so y minus 5 equals -3x, and then this point is -1. So y is going to equal -3. Distribute the -3, I get +3 plus 5, -3x plus 8. Okay, so then slope, so we can erase this. We don't need it. And then the slope, so the slope of A and C. So if we were to do this, we would go ahead and we would go, these 2 points. So we're going to go from 5. We're going from, 5 to 3. And then we're going from 1 to -1. So 5 minus 3 is 2. Divided by 2 on the bottom, we get 1. So this was just going to equal y. Oh, is it 3? Wait. No. Yeah. 5. This looks like it should be, yeah, that looks right. The slope should be 1. I don't know why I got the slope is equal to, oh my days. Okay. Now, y, so we're going to get y, I'm just going to keep rolling with this. I don't know how I got that. Maybe I'm doing this wrong, but it should be, so y plus, so this includes a 0.3, y minus 3 is going to equal x plus 1, so I get y equals x plus 4. Yeah, it seems about right. And then here, I get y plus 3, right, because I'm including 3, it's going to equal x plus 1, so I get y equals x minus 2. That doesn't seem right. Oh, it should be minus, that's why. So I get y minus 4. All right. Now I'm going to show you. We need to find transformations, right? I don't want you to really think about transformations, because transformations are like kind of at the heart of like how Jacobians and change of variables work, right? But really, you got to think of like transformations. That's still a linear algebra thing. You got to think of this in terms of Calc 3, right? We're still making a substitution. So how can we substitute? Remember, the easiest case is if we were to transform this into a square, right? Because in a square, you just have you just integrate by constants, right? You integrate from this constant to this constant to this constant to this constant, right? You're integrating like by constants. You're not, you can make it easier with that sort of substitution. That's what I want you to think of, constants. Take a look. I have a y equals x plus 4 and a y equals x minus 4. Look at this. If I rearrange, I get y minus x equals 4, and then y minus x equals negative 4. Look, I have these two terms. This y minus x term starts at 4, and then it goes to negative 4. This could be our u. Think about it. Because this would just mean if we set u equal to y minus x, that means u is going from 4 to negative 4. That would be akin to going from negative, if this was, our kind of UV plane, going from negative 4 to 4, right? Because this is y minus x, and then this, if this is our y minus x axis, it's a little bit unintuitive, but if we make this substitution for y minus x equals 4, that term is going from negative 4 to 4. So that becomes like kind of a constant. And think about this, right? If we rearrange this, we get y plus 3x equals 0, and then y plus 3x equals 8. Now, we could set this equal to v. We could say v is equal to y plus 3x. So, because we can make that substitution, right, that's the same as just this v term going from 0 to 8. So we just get this kind of square. We actually get a really nice square that we're going to integrate over. So, we just need to get u, we just need to substitute, we need to find x and y in terms of u and v so that we could substitute it back in. So if this is actually not too hard, you just gotta say, hey, y minus x equals 4, y minus x equals, it's just like a system of equations. So let's say right here, right? Let's say we know u is equal to y minus x, and we know v is equal to y plus 3x. Remember, I chose these equations based off seeing that certain terms go from one constant to another. If that kind of makes sense, you kind of need to rearrange and then find that sort of common term, whether it be y minus x or any other kind of function. So u equals y minus x, you could just, subtract these, right? Because when you subtract them, you get u minus v equals, the y's cancel, so I get negative x minus 3x, negative 4x. So I essentially get v minus u over 4 equals x. And then I can do the same thing now, where this time, if I have u equals y minus x, v equals y plus 3x, multiply by 3, and then I can just add, right? So I get 3u plus v is going to equal 4y, or 3u plus v over 4 equals y. So now I have these functions of, I have these functions of x and y in terms of v and u. So when I'm going to start doing my integral, the last thing is I just need to change, so I could even substitute this in, v minus u over 4 plus 8, 3u plus v over 4. the last thing is a dx dy, right? To transform it over, I need to find the Jacobian. Dx dy is just equal to the Jacobian times du dv. So to find the Jacobian, I just find the partial derivatives, right? So partial x partial u, right? It's going to equal negative 1/4. Partial sorry, I'm so sorry, wait. Partial x partial v, I don't know why I just blanked on that, is equal to 1/4. Partial x partial y partial u is equal to 3/4. Partial y partial v is equal to 1/4. Now I can find the Jacobian by taking the determinant, right? So if I take the determinant of negative 1/4, 1/4, 3/4, 1/4, I get negative 1/16 plus, or minus, I should say, 3/16, which is really just equal to negative 1/4, right? Right? Because I get negative 4/16, which is negative 1/4. But the multiplier is an absolute value. I don't know why. I think it's because something of how maybe the area is 1/4 as much, but it's a negative, so I don't really know how that works, but it's just the absolute value. So we're gonna have a negative 1/4. I'm gonna erase some of this stuff. We're gonna have a negative 1/4 kind of hanging out here. Du dv. So this is a case where the multiplier is not, or the Jacobian is a constant. So I can pull that out of the integral. And remember my bounds, right? I'm doing du first. I'm going from negative 4 to 4, and then I'm going from 0 to 8 based off these equations, right? If v is equal to y plus 3x, it's going from 0 to 8. If u is equal to y minus x, it's going from negative 4 to 4. So this, let's just dig in, right? So we can kind of get rid of this 1/4 here, right? Because there's a 4 and then a v minus u over 4. So this is just v minus u. And then I have this right here. So I'm going to have 2, 8 over 4 is just 2. So I'm going to have 2 times 3, which is 6, 6u plus 2v. It's 2v. Hopefully I did that right. And then you can see we could simplify this up. This is going to be 3v plus 5u. I might have messed this up, by the way. What was it, 3v? It was 3v plus 5u. Okay. Maybe I shouldn't simplify so much in one step. But I have negative 1/4, integral 0 to 8, integral negative 4 to 4. So we're going to have, if I were to integrate this, I would have, we're going from 3v and then u, right? And then we're going plus 5 over 2u squared from 4 to negative 4. Because this term is even, this term will actually cancel out when I substitute in things, right? Because I'm having 4 squared and then negative 4 squared, which is just going to be 4 squared. So this term will eventually cancel out. I don't have to worry about it. I essentially get, and then when I'm doing minus, right, it becomes twice as much. You know what I mean? Because I'm going to do 3v times 4 minus negative 3v times 4. That's just 6v times 4, right? So I'm going to have, it's going to be 6, it's going to be 24v. I really hope I did this right. 24v dv. I'm kind of brushing through the algebra because I want to save some time, but comment below if the algebra, you want me to clarify anything. So, oh, I said it's going to be the absolute value, right? Why did I write negative 1/4? Oh my days. Okay, so 1/4, and then we're going to go, we can pull the 24 out, so we just get 6. 6 times 0 to 8, so we're going to have v dv. This is just going to be equal to 3v squared from 8 to 0. So this will be 3 times 64, which is, I think, 192, I believe. Let's just check the answer key. Yeah, we get 192. So, yeah, this is an example of how you can do a change of variables. So one thing I want to show you is that we've actually done change of variables in double integrals and triple integrals before, right? Think about polar integrals. When we did double integrals with polar coordinates, that's a change in variables. We changed the dx. So let's just actually say this. So let's say we have, they give us an example, right? So the change in variables we've done in polar coordinates is we say, hey, let's say x is equal to r sine theta, and let's say y is equal to r cosine theta. Then what we say is like, okay, dx dr is just equal to sine theta. Dx d theta is equal to r times cosine theta. And then dx or dy d theta dr is equal to cosine theta. And then dx d theta or dy d theta is going to equal oh, did I get this backwards? I still got this backwards, didn't I? Oh my gosh. Let's just do this again, but with the actual proper thing. Okay, so dx dr is equal to cosine theta, dx d theta. This will be negative r sine theta, right? Because cosine theta, derivative is negative sine theta. And then we're going to have dy dr equals cosine theta. Dy dr is going to equal, what is dy dr going to equal? Sine theta. Why am I losing it? And then dy d theta is r cosine theta. When you take the derivative of sine, it's cosine. So now what we're going to do is we're going to take the determinant of all of these kind of terms, which is the Jacobian really. So cosine theta, negative r sine theta, r cosine theta. So if I were to take the determinant, I get r cosine squared theta, right, when I multiply the two cosines, minus, right, because when you take the determinant, you got to do minus, but then negative again. So plus r sine squared theta. And then you can factor out the r and you get a Pythag identity. So this just becomes r times 1, or r. So that's why dx dy is equal to r times dr times d theta, right? That the Jacobian is r. That's a term that goes in front. You can do the same thing for something like spherical integrals, right? Or spherical coordinates. For spherical coordinates, right? Remember we said that, okay, x is equal to rho sine phi cosine theta. Y is equal to rho sine phi sine theta. And then z is just rho cosine theta. Okay, this is about to get pretty algebra heavy, but essentially we're going to take a 3D determinant, right? Because we can find the partials. This is in terms of three variables. We can find the partial derivatives for each of the three variables. So for example, partial x, partial, oh boy, this is going to be kind of crazy, but it's fine. Partial x, partial rho is going to equal sine phi cosine theta. Partial x, partial phi is going to equal rho cosine theta cosine phi. Partial x, partial theta is going to equal rho sine phi negative sine theta. Okay, partial y, partial rho is going to equal sine phi sine theta. And then partial y, partial phi, or phi, whatever, is going to equal rho cosine phi sine theta. And then partial y, partial theta is going to equal rho sine phi cosine theta. Hopefully I'm not miscalculating these. And then partial z partial rho is just cosine theta. Partial z partial phi is 0. Oh, it's not 0 because this is actually phi. Whoopsies. It's going to equal negative rho sine theta, and then partial z partial theta is just equal to 0, right? Because it doesn't depend on theta. So we can take the determinant of this, right? So I'm going to actually, just to kind of save some time having to rewrite it, I can kind of do it like this and then get rid of these sort of equal signs and whatnots. Okay, perfect. So I can take this determinant now. To take a 3D determinant, remember, for example, for the first kind of term, I guess, you take this term, think of this term, right? You hide what row and column it's in, and you take this determinant, multiply it by that. And then you do minus, you hide the row and column, take that determinant, multiply by this, take this one, right? Hide the row and column, take this determinant, multiply by that. So if we go about doing this, oh boy, so let's do this. So this Jacobian is going to equal sine phi cosine theta. Times, okay, this becomes 0, and then this becomes minus, but we're going to make it positive because there's a negative. So this becomes rho squared sine phi cosine theta cosine theta. And then we're going to have a minus. We would have a minus. I'm going to just kind of guess this, right? We would have a minus for the second term, but then when I'm going to do this determinant, it's going to be this times that, which is 0, minus these two multiply, but then that minus cancel out the minus before, right? So we're just going to have a plus overall. So we're going to have rho cosine theta cosine phi. So if we were to do this becomes 0. So we're just going to have rho sine phi cosine theta squared plus, now we're going to have, for this term, this times this, so this will be a minus. So it's going to be rho sine phi sine theta. I'll leave it as a plus. So plus, and then you'll see it's going to be a minus because we're going to have this negative rho sine theta, okay, rho sine theta squared sine phi minus rho cosine phi sine theta cosine theta. Okay, this is a lot, in all honesty. But then I can pull a negative out here, so then this becomes a plus. Okay. When I distribute, we're going to do a crazy bit of distributing. So I'm going to get rho squared, oh boy, sine squared phi, right? Cosine squared theta, and then sine theta. Plus, I distribute this over, I get rho squared cosine cubed, which is crazy, by the way, cosine cubed theta, cosine phi, sine phi, minus, I'm going to get rho, okay, when I distribute this over, I'm going to get rho sine squared phi, and I'm going to get sine cubed theta minus rho squared, these are all squared, rho squared, I have this sine theta sine phi, or sine theta squared sine phi, and then times cosine theta, and then there's that cosine phi that's lurking. Oh boy! But what I can do is I notice each thing has a rho squared term as well as a sine phi term, so I can actually factor that all out. So rho squared sine phi, and we're gonna have to do a lot of cleanup, right? So yeah, let's go through this. So we're gonna have sine squared phi cosine squared theta sine theta plus cosine cubed theta cosine phi. Let's see if there's anything we can kind of do here. I notice I can essentially, let me think this through. No, I can't. I can't do that. Okay, let's keep going. Oh, this is really algebra heavy. Yikes, I might have made a mistake. Okay, here's what I'm gonna do, because I'm a little bit lazy, but also I don't think the average person needs to really see all this. Go through this and try to clean up the algebra. If I've made any mistakes, let me know. And if you want me a video going over this, I'll make one. But just to kind of not waste time, I'm just gonna leave it here. But thank you so much for watching. Hopefully this has cleared up some mysteries on Jacobian.